Okay, here we go. Let me try this. Oh, that scared me. Oh, well, that's better. And no more music. Okay, hello, wonderful person and people of all sorts from everywhere. So welcome to your, I guess, annual stream, sort of, even though I keep promising to make these at least monthly. I'm going to double check that everything is working before we start. And also, I think we still have about 30 minutes before the official announcement, which is what we're going to be doing today. But let me see. Okay, here we go. Everything seems to be working. I'm going to hear myself for 1 second. Let me hear myself for 1 second. Where am I? Where's my stream? Let me see. Okay, here we go. All right, seems to work. Let me know if there's a problem or problems. I'm sure there will be problems because I have not done this in over a year. The last time we did this was during the 2024 solar eclipse. And now we're back. And I promised last year that I was going to do a stream sometimes in the summer of 2024. Never happened. My apologies. Anyway, so what is, first of all, to answer your questions, still not AI, as you can see, still 10 fingers. Second of all, what are we doing? So today, the main point of this stream, the annual stream, is because we actually have a huge announcement from the National Science Foundation, the Vera Rubin Observatory, and basically it is going to be about, let me check, how do I disable this? It's going to be about this, no, come back, here we go. It's going to be about this. We have half an hour before the announcement from Vera Rubin Observatory, and I don't exactly know what they're going to be talking about yet, but it's basically going to be most likely the discussion about the first images that were just released and possibly some more images, which is what I'm hoping for. And so they basically asked for anyone who has any following to do a kind of a impromptu party, I guess. And there's actually a whole list of parties they have listed here somewhere. Here we go. Let me show you some of these parties. Host a Rubin party is what it's called. You can actually see some of them are possibly in your neighborhood. And, oh, where's the map? I thought it was a map. There has to be a map somewhere. Oh, I thought it was a map. Anyway, I saw a map somewhere. Anyway, so this is one of these parties, but it's basically virtual and not in person. And the point is to look at the images, discuss them, and just to basically get ready for the mission that Vera Rubin Observatory is going to be performing for the next decade. And it's going to be a huge mission. So that's what I'm going to be talking about. I'm going to try to simplify the mission as much as possible and talk about why this is probably one of the most important observatories of the last few years, really, possibly of the last decade. Maybe even more important than the James Webb, just because of the actual quality of pictures we're going to be receiving. But still, James Webb is still pretty important. All right, so let me just set up some of the background pictures I had here, just until we wait for the announcement. Also, this is what it looked like a few years back. This is when they were building it. This project took approximately 20 years to finalize. And this is a pretty big observatory, and it has one of the biggest telescopes with the most sensitive camera in the world. So take that, Samsung. Samsung phones have nothing compared to this. And what am I looking for here? I'm looking for my display picture. I don't need this right now. All right. While we're waiting for everything, I was going to briefly talk about the mission, I guess, and take some questions. Then we're going to listen to the announcement from Vera Rubin because I actually am super curious to hear what they're going to be talking about. And lastly, we are going to finish with a Q&A, or maybe just Q, maybe no A, because I don't have all the answers. Anyway, so hello everyone from Canada and from other countries. And let me see if there's any comments that I need to answer to yet. Any questions? Cool. All right. If there's any problem with sound, or if you cannot hear something, or if there's a music in the background, please let me know, because I'm still, even after years of doing this, I still forget to turn off things, to turn things on and so on. And in the meanwhile, while I'm waiting for the stream to start, which is going to start in about 27 minutes, I wanted to briefly mention what this telescope is, I guess. because it is a pretty exciting telescope. And it is called Vera Rubin telescope because of this wonderful lady. Let me just get this checked. This wonderful lady is Vera Rubin. She unfortunately passed away, I think about 7 years ago. I think it was 2018. And she is considered to be, I guess, unofficial mother of dark matter. Even though I always get comments about, oh, this guy still believes in dark matter, blah, 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 blah. Well, she did too, but even though she wasn't sure what it was. And she was the one who essentially kind of sort of found it by looking at galactic curves of Andromeda Galaxy and a few other galaxies. She was the one who basically brought it to everyone's attention and was supposed to get a Nobel Prize, but never did. And because of that, a lot of scientists were upset. Instead of Nobel Prize, she got this. She has a telescope named after her, which I personally would take over Nobel Prize too. The reason this telescope is so important is really because of just the sheer quality of the lens, the sheer quality of the mirror, the camera, the actual camera it uses. I'm going to show you one of the pictures that I have here somewhere. I have a bunch of pictures actually, but I didn't prepare at all for this. I just found pictures. I'm like, oh, I think I'll figure it out. Here we go. Here's another picture. This is a picture of the telescope on the mountain, and this is located in. Let me try to read the name of this mountain. It's called El Peñón Peak of Cerro Pachón. It's a 2,700 meter high or about 9,000 feet high mountain in Coquimbo region of northern Chile. And this is very close to other famous telescopes like Gemini South and Southern Astrophysical Research Telescopes in the Atacama Desert in Chile. And it's essentially located here for one simple reason. They have the best night skies in the world. And they barely get any rain. They have the best visibility, and most of the modern telescopes are in the same region. It's the Chilean government managed to find a perfect niche for their supplements, for the government supplements. They get a lot of money from these projects. And so this is the new creation, and it's basically going to be one of the most powerful Earth telescopes, optical telescopes, that's going to be doing its mission for the next 10 to 12 years. Okay, so let me just double check. I haven't been reading comments yet. Let's see. Okay, let's see. Comment number 1. I think I have a comment. Oh, thank you for the donation. Solar Night. Can you elaborate a bit about the current solar maximum flares, Parker Solar Probe possible Carrington event? It's not really related to this, but okay, I'll try to elaborate. Nothing to worry about. There's not going to be any possible Carrington event anytime soon. The solar maximum has passed already. The sun is currently going toward its minimal peak. It's basically on the way down. So we don't think anything major is going to happen anytime soon. And Parker Solar Probe is still doing its mission. It's basically still collecting data. It's done its recent close passage, but it hasn't really discovered anything major yet. There will be an update about this, I think, in about a couple of months. But we'll talk about it in some other videos. Parker Solar Probe, even though it's an amazing mission, it does collect data very slowly, so it takes a long time to process everything. So we don't really have that much information yet. But it's supposed to solve the mystery of basically why we get these CMEs, coronal mass ejections, and how the solar magnetism works and so on. It's one of its main missions, so we'll hopefully get some cool answers very soon. All right, cool. Thank you for the question and for the donation. Love it. No, the donation is great, but I'm loving the questions. Okay. Next question. It's a good question. Ground-based telescopes, if they're so good, why do we need space telescopes? Well, remember, on the ground here, we have atmosphere, right? So not all frequencies pass through the atmosphere. The atmosphere is opaque to a lot of different wavelengths. And one of them is, of course, infrared wavelength and also ultraviolet. So if you want to see things in the infrared, you absolutely have to have a space telescope. And the only reason we want to see infrared is because according to the Big Bang Theory, which is, of course, still has not been disproven by anyone, even though there's a lot of AI videos that claim otherwise, according to the theory, the ancient, super ancient stars, super ancient galaxies were all essentially producing a lot of UV light, but because of the redshift, because of the expansion of the universe, due to the Big Bang, the wavelength from those stars has now decreased to the infrared frequencies. So if we want to see those super, super ancient stars and very, very powerful galaxies, we have to see infrared light today. And that's why space telescopes like the James Webb are essentially absolutely necessary for that, to essentially prove these different propositions and hypotheses that we have. Such a difficult word. Anyway, next comment, question, concern. Is this telescope using a laser tag to autocorrect? So the interesting thing about this telescope is that, as far as I'm aware, it does not have any autocorrection. It does not correct for atmospheric interference because it's not able to. The way this is designed is that, unlike typical telescopes that focus on just one point where you can kind of autocorrect using lasers, this one has a very, it's actually essentially the first telescope to use a very wide view. And that's what makes it so interesting, because normally you have telescopes that are either wide view or super focused. And we don't really get a lot of telescopes that can do both. This one, though, can, because of the way it was designed. So it has an enormous mirror and a very sensitive CCD sensor, and it's able to collect a lot of data, but it doesn't autocorrect using lasers. I think they're using some kind of algorithm. I hope maybe they'll explain it during the stream, but I don't know the details because I'm not a technician and not familiar with the actual technology. So I'm sure there's something going on that's going to correct it a little bit, but just not as much as a modern telescope that uses the laser correction system, which is usually why, if you ever see a picture of a telescope, let me see if I can actually find one. Telescope laser. You usually get these like pictures of, laser guiding systems. So that laser stuff, that's to autocorrect for atmospheric interference and to guide telescope towards certain locations. This one is not going to be doing that. This one is just going to be sitting there and collecting a lot of pictures over and over and over and over again, and they're all going to be absolutely amazing. Okay, Gianninta, thank you for the donation and also a question, I guess. Good evening. I never missed your single video since 2019. You've been my main source of science news ever since. Keep up the good work. Thank you so much. Not a question, but thank you so much. I appreciate it. All right. Cool. I hope I didn't miss oh, something's happening. Nothing's happening yet. Okay, we have 20 minutes. Right. So let me see what else I wanted to mention. I also wanted to mention that this telescope has several primary missions. Unlike previous telescopes that would only focus on maybe one or two things, this one actually has a variety of missions that are going to be quite difficult to achieve at first, but it has 10 years to do it. So first of all, is obviously is going to study dark matter. The way it's going to be doing it is through the effect known as weak gravitational lensing. So let me just see if I can find it. Didn't find a picture for that in advance. So it's essentially, so this is the strong gravitational lensing. This is the effect where we know that certain masses produce gravitational lenses, and this is the Einstein lens. We know that this is the effect from both mass and dark matter in this object, inside this galactic cluster. But it's going to be, here, this telescope is mostly going to be focusing on the weaker effects. So the ones that are kind of difficult to see, but they're still there. And it's going to use a lot of different pictures that it's going to be collecting over the next 10 years to essentially assemble this kind of a map of dark matter. No matter what it is, we have no idea what it is. We know it's there. The effects are there. The mystery is there. We just don't know what it is. We don't know if it's a particle. We don't know if it's a formula thing, which it probably isn't because it's been disproven several times. We don't know if it's some kind of a strange fifth dimension, multi-dimension thing. We just know that it's there. And it's undeniable. It's been proven many times. It's just, nobody knows what it is, though. It's just that it's there. And that's one of its main missions. It's also going to try to study dark energy, which is mostly a mission for another telescope, another mission known as DESI. We've discussed this in some of the videos. Or you can just type DESI, D-E-S-I. You'll find the actual mission pretty quickly. But yeah, dark matter, dark energy, weak gravitational lensing. What else? We have the concept known as baryon acoustic oscillations, also known as BAO. That's a pretty cool concept, but it's kind of hard to explain it in 5 minutes. So I'm going to possibly post some links in the description from previous videos that talk about it. But it's essentially these ancient bubbles from the beginning of the universe that seem to be everywhere, but it's really difficult to find them and difficult to see them. We just think and know they should be there. And this telescope is going to be really, really good at detecting them. And also, it's also going to be really good at detecting various transients, which is basically short word for explosions. Any kind of a change of light, like for example, sudden nova, like the one we just talked about in the video today. In case you haven't watched the video, there's actually a nova in the sky. You can see it with the naked eye. There is also, what else? Any kind of asteroid passage is going to be able to see. Any kind of a comet is going to be able to see. It's going to be able to detect minute changes in light. And so researchers behind this telescope actually expected to find an enormous amount of near-Earth asteroids, like the amount we've never even imagined. We're talking about, instead of finding hundreds per day, we're going to be finding like thousands, if not even millions. And it's going to be able to find a tremendous amount of objects we just could not see before because it's so sensitive. And because this telescope has a wide perspective, it's going to be able to capture so many pictures at once and then compare them within just like a few days or so. So it's going to be pretty good at detecting a lot of different changes in the night skies, which is something we've been waiting for a long time. All right, let me show you something else here. I was going to show you this picture I showed you. Oh yeah, that's a picture of Vera Rubin, go back. The lady who this telescope is named after. So she is probably one of the most well-known researchers when it comes to dark matter. And here is the picture of the actual sensor. Like you have a camera sensor in your camera. So that's the sensor they have in this telescope, and it actually looks like this if you look at it. Where is it? Where's the picture? I had some really cool pictures I found of someone holding the sensor in their hand. I just can't find it anymore. Where are you? Where are you, picture? Okay, that's the telescope. I don't need that one. Oh, that's the mirror. That's how big the mirror is. I think it's over. What's the exact size? I have the exact size somewhere. It is exactly. It's 8.4 meters, which is. Google, help me. What's meters and to feet? It is 28 feet approximately. So this is pretty big. It's a pretty big mirror. And the sensor is also very big as well. So yeah, it's a massive telescope. Not the biggest, but it's going to be the most sensitive because of the combination of the mirror and the sensor. And back to questions, if there are any. Did I miss anything? Okay. Okay, questions. I'm looking for the question marks. Is the 10 to 12-year mission time standard? It's not. It's just this is the minimal time for the mission. They're hoping for more. It basically depends on the funding. You might have heard that we don't know what's going to happen with the funding for the National Science Foundation. So they already have 800 million prepared for this for the next 10 years. That's the 10-year mission plan. But if there's more funding, they'll be able to continue it indefinitely. Unlike space telescopes, this one can be expanded, it can be repaired, it can be improved. So that's not really an issue for the mission on Earth compared to a space telescope like James Webb. James Webb does have a mission limitation just because it's in space, so we're unable to repair it and we're unable to fix it if something breaks. Okay. Okay, someone's asking about a white hole. White holes, no, never detected. Sorry, never seen. Next question or concern. Do I think we'll ever inhabit Mars? Not really, probably not. Sorry, also sorry. We'll probably send some robots and automated missions, but like, what would you do on Mars? It's not fun, and also there's probably no way back if you land. So. Not for a while at least. Definitely not this generation. Maybe in a few generations from now if we get a little bit smarter, but not yet. Cool. So how are we doing here? Hasn't started yet. Good. So I was going to go through. Oh, here. Let me show you one of the first pictures. They're probably going to be showing this too. So this is what it's capable of. Let me just remove my face from here. What you see here is the most detailed picture of one of the most famous clusters, Virgo cluster. I want to show you what it looked like before. This is the before picture. This is from I think a few years back when they took it with the DSS survey, I think. This was This is from the European Southern Observatory. And now the same picture kind of looks like this. So absolutely mind-blowing detail, like just insane amount of detail. And here we'll be able to see things we have never seen before from the ground. Just ridiculous detail. I'm sure they will mention more about this because I didn't really get any detail either. I mean, I got a picture, but that's about it. Hopefully, when we have the official stream from Vera Rubin Observatory, we'll get to hear and see more. But the reason this Virgo cluster is important is actually because this is one of the few clusters where we definitively see effects from dark matter, and it's really important for dark matter research. And so by seeing more, we'll be able to, scientists will be able to tell what's going on here. The black dots on the other picture, that was most likely just from the telescope blocking the view. Certain telescopes have limitations. Okay, cool. What's going on next? What else do we have? So, what do we know about this telescope? Well, first of all, we know that the actual planning started back in the late 1990s. And by early 2000s, they actually started building it. So it's been in construction for a very long time. The main mission is it's sort of a continuation of the survey missions. The official surveys, like the first surveys, I guess, started like over 150 years ago with what we used to call photographic plates. So astronomers used to take a look at like a spot in the night skies. They would take a picture, not a picture, but a photographic plate of that particular location. And then they would do this one after another, and keep them in some kind of a library somewhere. I think Harvard actually has one of the biggest ones. And these photographic plates were super important for discovering a lot of things about astrophysics. For example, that's how Edwin Hubble was able to prove that the universe even existed, because he looked at a photographic plate of the Andromeda galaxy and he discovered a tiny spot in there that turned out to be a very important star. And that star had to be super far away for this to be real. And that gave him sort of a clue that we're looking at something super distant. And so the universe must be massive compared to what scientists thought before that. So photographic plates is how it all started. But by 2000s, we had automated surveys. And one of the most famous ones is called SDSS. Let me see if I can get a website for this. Or not. Didn't work. Okay, let's try again. SDSS is here somewhere. Yeah, Sloan Digital Sky Survey. So that's our first. Come back. Where are you? Here, SDSS. So that's one of our first automated surveys, and it was pretty good. It's still used today by a lot of different astronomers. This basically collected a very, very large amount of, I guess, equivalent of photographic plates, but digital photographic plates across the night skies, and created kind of a map of the night skies for us. But because it was not super high quality, this is why researchers needed something better. And that was the birth of this particular telescope. So it's going to be the most accurate, the most, what's the other word? Basically the biggest map of the night skies, but unfortunately only the southern skies, because it's in Chile, so it's only going to be focusing on the southern hemisphere. So we need to have something similar in the north, but unfortunately there's no similar location in the north, unless I guess someone builds it somewhere in like North Norway or something, but hasn't happened yet. And for the next 10 years, it's going to be taking advantage of the Chilean night skies, which are usually supposed to be super clear and brilliant, and some of the darkest nights on Earth, actually, to conduct a very large astronomical survey, more ambitious than any previous scientific project. And one of its goals is also, except for dark matter and stuff, it's also going to be studying near-Earth asteroids, which is actually a lot more important for, I guess, Earth defense. When it comes to Earth defense, we need to catch as many near-Earth asteroids as possible. You might remember the story from about like a few months ago, the asteroid that was discovered at the last minute, the 2014 YV4, that was possibly colliding with Earth, but suddenly was colliding with the moon after that. So that particular asteroid was discovered at the last minute, but according to the researchers that were creating this telescope, they basically said that we would have found it a long time ago. So it's going to be able to do all of this pretty quickly. Oh my God, someone gave a lot of people memberships. Thank you so much. How do I? Wow, 50 memberships. Thank you, Lucas. Amazing. Wow, that's amazing. Thank you so much. And thank you, Yuri, for donating 10 euros. That's also my son's name. Anyway, so what was I talking about? Yeah, so asteroids. We're going to be finding a lot of asteroids, a lot of comets, a lot of stuff in the solar system. So for Earth defense, it is going to be this mission is going to be absolutely essential. And there's also hope that if Planet 9 is real, which a lot of scientists now doubt, based on the video I made a few months ago, where there's a team that discovered a dwarf planet that potentially proves Planet 9 wrong, Planet 9 hypothesis. But anyway, so if it exists, this telescope should be able to see something somewhere out there. If not, then well, too bad. Anyway, hello and welcome everyone, whoever just arrived to this stream. If I'm starting to struggle pronouncing things and talking very slowly, it's because it's almost midnight here. As some of you know, I am actually in South Korea right now, so it is going to be pretty hard for me to talk after 1 a.m. Mostly because I'm so tired. But we have about 5 minutes before the stream starts. I'm going to, in about 5 minutes and 30 seconds, I'm going to shut up, and we're going to listen to what the stream by the Vera Rubin Observatory has to say, because their stuff is going to be really important, or I guess more important than what I'm saying, because I'm kind of curious to hear what they have to say too. Anyway, so apart from the near-Earth asteroids and all kinds of Kuiper Belt objects, this mission is also going to be looking or finding a lot of different nova, supernova, all kinds of transients. We're going to be seeing way more explosions in the night skies than we ever could before, because of the way that it's going to be taking pictures after pictures and comparing them. So it's going to be able to detect a lot of transients in the night skies. And that's going to be super exciting. And one of its missions is also to map our galaxy. It's going to be mapping the actual materials in the Milky Way, contributing to the previous discoveries by the Gaia mission, and which actually makes it a little bit different from other telescopes. So we do have some other powerful telescopes, like I mentioned, the mission known as DESI, Dark Energy Survey Instrument, and that one is kind of doing something similar, but it's looking everywhere but the Milky Way. So it's basically looking at other distant galaxies. It's looking at galactic clusters far away. It's ignoring most of the stuff in the Milky Way. This telescope, though, is going to be looking at everything, including the Milky Way. So this is why it's a little bit more intriguing, more interesting. There's basically has like a collection of different things that's going to be presenting to us, and someone out there is going to love it, no matter what it presents. It's going to be a bit of everything for everyone, which is going to be super exciting, I think. Basically, it gives me a lot of hope, because nowadays it's kind of hard to find exciting topics to talk about, especially due to a lot of budget cuts. Not a lot of good science has been going on in the last few months, but this will probably change it. So we'll have a lot of stuff to talk about in the next few months. Okay, what's going on? Let's see. What did I miss? Grover, thank you so much for the donation. And how much data will the sensor be able to capture? Is it near real-time capture? So that part I don't know, because I know just as much as you when it comes to the actual technicals. I just know that it's supposedly going to have at least 10 times more capability compared to previous surveys. So I think actually, if you look here at the preview, it kind of shows you the visual representation of this. Let me see. So in a nutshell, as far as I know, it's supposedly going to be able to capture approximately, where is it? Hold on, let me find it. I forgot how many exact images it's going to be capturing. Oh, come back. So every 30 seconds it's going to be capturing a picture somewhere out there. And it's going to be pointing the researchers are going to be pointing the telescope at slightly different parts of the night skies. And they're going to be able to capture huge areas every single day. And so basically, after every single day, they're hoping to capture as much as possible, and do this over and over and over again, just in order to find various transients, in order to find slight deviations, which might be different asteroids and so on. Also, wait, what else was it? So is it a near real-time capture? The actual capture is real-time, but the data is obviously not going to be accessed in real time. As with most telescopes, the amount of data is just absolutely ridiculous. So it will probably most likely have to be processed first. And then, like maybe after a week or two, possibly a few months, we'll start getting some processed data that the researchers can use for actual detections or for research. Like there was something, I'm trying to remember which telescope it was recently. There was a telescope that suddenly released a lot of data for everyone. And we had an enormous amount of papers coming out just because the data was kind of stuck and unprocessed. So once the data is processed, usually you get a lot of papers at the same time. But in terms of how much data, a lot. I don't know exactly how much, but a lot. It's way more than James Webb for sure. Oh yeah, here it says in this picture, I think. One image would need 4K high definition TVs. So whatever that means in terabytes, or gigabytes. So basically a lot. The actual technical parts I'm not really familiar with. Okie dokie. What's 42 seconds? Okay, we're almost there. Okay, so let's see. Once they start talking and once there's something here that needs to be listened to, I'm going to switch. I'm going to turn myself off and I'm going to let them do the talking because this is an exciting stream. We only get these like once a year, so it's interesting to listen to this kind of stuff. Do we know what frame rate it is? It's not really a frame rate because it's just still taking pictures. So it's one picture per frame, but it will be creating these huge maps though. So and the maps will be changing slightly. It says every 4 nights approximately is going to be changing the entire night sky. So yeah, so I guess it's 2 frames per week. There we go, 2 frames per week approximately. So that's the approximate frame rate. Does Vera Rubin Observatory have continuous live streams from a website? I don't think so. I don't think they actually do this because you have to remember it is still in a remote location, and they do need all of the possible data that they can get for the actual sending out the processed information and stuff. So I don't think they have a live stream, but I might be wrong. Some telescopes do have a live stream, not of the actual night skies that they're looking at, but just like of, I don't know, parking lot from the outside or whatever. Normally, these types of telescopes, they don't have actual live streams, unfortunately. Although I'm sure if someone can figure out how to do it, that'll be great. So someone actually asked a great question. D-Lay H. Thank you so much for your donation. And the question is, how do they distinguish thousands of asteroids from thousands of satellites? And that is actually the biggest question that just came up recently. So there is an algorithm that they use to try to avoid detections of various satellites, especially because of all of the internet-based satellites we have today. Oh, something's happening. I'm going to turn myself off in 5 seconds. But anyway, yeah, so the long story short is that it's an algorithm, but it is a huge issue. And I'm sure they'll mention it, and if not, I'll talk about it after we get to watch this. Let me see what to turn this on, how to turn this on. I need to turn this off. I need to turn this off. I'm going to come back in a couple of minutes. Let's see what they talk about. And I'll be back in maybe 5 minutes.
Observing across space and time. Bringing the night sky to life. The universe awaits.
Welcome, welcome. On behalf of my colleagues at the National Science Foundation and the Department of Energy's Office of Science, I welcome everybody here and all those streaming online. This day marks a very special occasion, revealing and celebrating the first look at the universe through the eyes of NSF DOE Vera C. Rubin Observatory. As we begin to bring online priority for ground-based astronomy in the National Academy's 2010 Decadal Survey. We trust that you will enjoy this tiny peek at the many discoveries to come, and we are very excited to show you. I am Edward Ajar, the NSF Program Director for Rubin Observatory. Before we begin, I would like to thank the National Academies for providing this beautiful venue and excellent support for this occasion. And now, it is my pleasure and honor to introduce to you Brian Stone, NSF Chief of Staff, performing the duties of the NSF Director. Please welcome Brian Stone.
Well, thank you, Ed, and thank you to all of you for being here today. Starting today, our ability to understand dark matter, dark energy, and planetary defense will grow even faster than ever before. This exciting new future is thanks to the vision, work, and support of the many people we're proud to recognize here today. Let me begin by thanking the White House Office of Science and Technology Policy Director Michael Kratsios and the administration for their continued support of exploratory science. By working across federal agencies, OSTP, NSF, DOE, we turned shared investment and coordination into a transformative interagency public-private partnership. The flagship observatory has been more than 20 years in the making, with NSF behind the project every step. NSF brought together a coalition of partners to build and support the cutting-edge facility, instrument, and data management systems. More than 40 international organizations contributed to building Survey Telescope with the ability to gather more data than all other ground and space-based optical telescopes in history combined. NSF is proud to continue to lead Rubin's operations as it begins to deliver on its promise to expand our understanding of the universe. Thank you to DOE, our international partners in Chile, private donors like Charles Simoni, the National Academies for prioritizing Rubin in the 2010 Astronomy and Astrophysics Decadal Survey, and the entire Rubin team, especially Tony Tyson, Rubin LSST chief scientist who conceived and championed this project from the start. Vera Rubin is the namesake of this facility because she is the symbol of scientific excellence. Her legacy reshaped astrophysics and our understanding of dark matter. Generations of researchers have been and will continue to be inspired by her. Alan Rubin, one of Vera's children who's joining us here virtually today, once told NSF, Vera believed there is always more to be discovered. So let's keep discovering together and proving her right. Now I hand it off to Kathy Turner from the Department of Energy. Thank you.
Hello, everybody. We're incredibly thrilled to be here today for the unveiling of these new images from the groundbreaking NSF DOE Vera C. Rubin Observatory. Just a preview of the data to come. I'm Kathy Turner, Program Manager for Rubin Observatory from the Department of Energy Office of Science. Carrying out this project in partnership with NSF and the private and international partners has enabled us to bring all of our strengths to this amazing observatory. I am honored to work with all of them and look forward to our continued partnership. This observatory represents a giant leap in our ability to explore the cosmos and unwrap the mysteries of the universe. Of great interest also to the observatory's namesake, Dr. Rubin. Now I'd like to introduce Harriet Kung, our acting director of the Office of Science at Department of Energy. With decades of experience in scientific leadership, her vision and dedication have been instrumental in making this amazing observatory a reality. Please welcome Dr. Kung.
Good morning, everyone. Thank you, Kathy, for the wonderful introduction. On behalf of the U.S. Department of Energy, let me add my thanks to the long list of organizations that has made today's event possible. First of all, national academies. I would especially like to single out the Board on Physics and Astronomy and also the Space Studies Board for hosting us in this beautiful auditorium today. I also want to thank White House OSTP, the National Science Foundation, and also the Association of Universities for Research in Astronomy, as well as my colleagues in DOE's Office of Science, for putting together the wonderful program that we'll witness today. But let me first introduce a short video from the Secretary of Energy, Chris Wright, who is not able to join us today, but he took the time during his recent visit to SLAC National Accelerator Laboratory to film the video you'll be seeing shortly. So let's cue the video.
Today we celebrate the culmination of 2 decades of scientific and technological innovation that have given us an ability to look into the cosmos, to understand our universe itself. This is the Vera Rubin telescope in Chile, and I want to congratulate all of those at the Department of Energy and the National Science Foundation, those working at SLAC out here in California, where I'm standing right now, and those on the ground in Chile, for this tremendous technological achievement that truly will bring an understanding of our universe simply not possible before. The movie has started, the camera is running, and we're going to see our cosmos unfold before us. Congrats to all.
Thank you, Secretary Wright. Having this event today really feels like a homecoming. It was really the 2010 National Academy Decadal Study for Astronomy and Astrophysics that recommended that our high-energy physics program partner with NSF on what would become the Rubin Observatory, which was the number one top-ranked ground-based project. As Brian has already mentioned, the NSF DOE Vera Rubin Observatory was a project long in the making with many moving parts. The DOE's Office of Science was proud to lead the construction of the LSST cam, the largest digital camera ever built. It is the size of a small car, but twice as heavy. The camera, boasting an impressive 3,200 megapixel resolution, was lovingly designed and fabricated by scientists and engineers at SLAC National Accelerator Laboratory, with critical contributions from DOE other national laboratories, as well as international partners. This camera, in conjunction with the Simone Survey Telescope, will create a 10-year survey of the sky in the Southern Hemisphere, known as the Legacy Surveys of Space and Time. This treasure trove of data set will give researchers unprecedented depth and clarity to questions that drive the fundamental research supported by DOE's Office of Science. And some of the questions include, how can we better understand the matter and energy that makes up 95% of our universe? And why is our universe ever expanding quickly, and how is that pattern change over time? And also, what role did dark matter play in how our universe evolved? We anticipate that the observatory will give us many insights into our past, our future, and possibly the fate of the universe. Answering these questions is a challenge that is matched with the many, many talents that contributed to today's success in the survey. We at DOE are extremely proud of the many people that have contributed to this amazing project. We're especially grateful for the indispensable cooperations from our international partners. In particular, the success of the Rubin Observatory relies on its location high atop Cerro in northern central Chile. That's why I'm so pleased to introduce to you His Excellency, the Ambassador of Chile to the United States. Ambassador Juan Gabriel Valdez has dedicated his career to fostering strong ties between our nations. Please join me in welcoming Ambassador Valdez. Thank you.
Good morning, everyone. Mr. Michael Kratsios, Director of the White House Office of Science and Technology Policy. Mrs. Harriet Kang, Acting Director of the Office of Science at the Department of Energy. Mr. Brian Stone, performing the duties of the Director of the National Science Foundation. Distinguished American and international authorities, esteemed scientists and friends of the National Academy of Science who welcome us today. I'm very happy to be here today. I have to say that I have received a number of calls from our friends, astronomers in Chile, saying that I had to be here today. Therefore, it's a fortune to be representing them this morning. Chile is without a doubt an astronomical nation. Evidence of astronomical observation by our earliest inhabitants dates back more than 2,000 years before Christ. Our geography gives us clear, dry, and stable, ideal skies for observing the stars. Astronomy is part of our identity and our heritage, and we are proud of it. But it is not only nature that has led us to become global leaders in astronomical observation. It is also the result of our government decision, a clear and sustained policy of international cooperation, scientific development, and the protection of our dark skies. Today we celebrate the first images from an extraordinary telescope, the Vera Rubin Observatory, equipped with the largest digital camera ever built for astronomy. But we also honor the memory of an extraordinary woman. Vera Rubin was not only a pioneer who uncovered key evidence of dark matter, she was also an inspiring example of integrity, perseverance, and humanity. Vera Rubin pushed the boundaries of scientific knowledge, but also her era. Naming this observatory after her is a profoundly symbolic and just act. It sends a message to new generations, and especially to the children and young people of Chile and the world, that knowledge has no gender and that the university is open to all. Vera Rubin has been the inspiration for the important and growing number of women astronomers we have in our country. For Chile, the observatories represent our commitment to knowledge, to sustainable development, to international cooperation, and to the defense of dark skies.
Okay. I did not expect so much dialogue. I know some people are getting restless. So am I, unfortunately. So how is everyone going? I actually really didn't think there would be so much politics too. Let me just mute this a little bit. There's a lot of dialogue, a lot of introductions. This is very different from what it was like for the James Webb or the Martian missions. Here they do have a lot of things they want to say. Anyway, while they're talking, while they're thanking each other, let's briefly go through some of the questions, or possibly maybe some concerns. Or by the way, please be nice. Yeah, someone already had to be muted because of the comments they were making. So don't be mean, or I'll mute you. What am I doing here? All right, let's go through some of the facts I wanted to mention while they're talking. Also, let's see. Okay. I have it in my ears. I'm going to make sure that we don't miss anything. So I'll switch to the stream once they start announcing the pictures, because that's what we're here for. Oh, okay, wait. I think he stopped talking. One thing I actually forgot to mention is that... Oh, what's happening? Hold on.
Kratio, director and assistant to the President for Science and Technology. Director Kratio previously served as Chief Technology Officer of the United States during President Trump's first term, where he advised the President on landmark initiatives in artificial intelligence, 5G, quantum computing, and advanced manufacturing. Looking back, many of these initiatives not only had launched, but have
Okay, I'm back. I think they're going to be talking for a while. My apologies if you actually want to watch this. The link for the actual stream is in the description. So I would like to focus on actual science, not political introductions. So if you do have questions, please ask. Well, one thing I forgot to mention is that there was actually a sneak preview of one of the short videos they made, or short pictures. Hopefully they'll show it to us here as well. And apparently this was done with 1,100 images. And it eventually actually showed us approximately 20 billion different objects in the image itself. But I don't know if we get to see this today. Wait, where did it go? Where are my comments? Here we go. All right, here we go. I think I have a question. Can you explain for a second who Vera Rubin was? Thank you for the donation and for the question. QLCS Appreciator. I appreciate your question. So she was a graduate student in, I forgot what university it was, who was essentially working on studying different galaxies and studying galactic curves of galaxies. And I want to quickly show her picture in case you've never seen who she was. The coolest picture of her is actually here somewhere. Here. This is probably the coolest picture that I think is so far at least. So here she's working on one of the telescopes. Where was this? Sorry, I forgot where this was, but let me see. It probably says it here somewhere. No, it doesn't say here. Anyway, so she was a astronomer studying galactic curves, and completely by accident, she discovered that something in those galactic curves refers to the way galaxies spin, rotate. So normally, galaxies, they spin pretty slow, right? But we have ways of measuring their rotation speed by looking at the redshift and the blueshift of various parts of the galaxies. And in essence, if you were to simulate this, it kind of looks like this. Here. Here's what it sort of looks like. So we always expected galactic curves to look this way. Essentially, we think of a solar system, right? In the solar system, planets like Mercury will be spinning around the sun much faster. Planets like Earth will be spinning a little bit slower. Planets like Jupiter will be spinning much slower because they're much farther away from the sun. And that's what was expected of galaxies. And when she looked at those galactic curves of several different galaxies, including the Andromeda, she found something completely different. The entire galaxy was spinning as if it was a disk. Like it was literally, the actual curve was flat. And because of this, she by herself, she kind of started doing a lot of measurements and discovered this in a lot of different galaxies. And her explanation was that there must be something in the galaxy that we're not seeing, some kind of a dark matter that is making the galaxy spin this way, because it made no sense. Otherwise, the galaxy would basically fly apart completely. And so she was the first to kind of bring it into attention. And ever since then, for decades really, this was studied over and over, and it was confirmed by many different astronomers. And so she was the one who discovered it. But the reason unofficial reason the telescope is named after her is because of this discovery, everyone expected her to get a Nobel Prize, and she didn't. And she passed away without any, acclaims, anything, nothing named after her. Nothing really important was kind of surrounding her legacy, and a lot of scientists were super upset about this. And so this telescope, which was originally known as LSST, I think, what was the name of the telescope? It used to be known as Large Synoptic Survey Telescope, LSST, Large Synoptic Survey Telescope. That's the name of the technology it's using. So a lot of scientists basically sat together and voted on it and decided we're naming it Vera Rubin Telescope because she deserves to have something named after her. And so a year after she passed away, it was officially announced that this is now going to be known as Vera Rubin Telescope, because one of its missions is, of course, to study dark matter. So there you have it. That's kind of who she was, and that's the main mission behind it. Unfortunately, I was really expecting to talk about it because that's such an important part of legacy. I don't even know enough about Vera Rubin myself to explain. Obviously, I've never met her, unfortunately, and she was super old by the time I became interested in astronomy. So she wasn't. I don't think she was doing research by then. Anyway. If you have any questions, let me know. I'm going to be going back and forth in between their stream and I guess my stream, but I'm mostly focusing on scientific questions and anything you want to know about, I guess, the universe or dark matter or whatever. And please don't be mean, and so on and so forth. And also. Oh, okay. There's another question. There's another question from Gary Scarana. Why are some galaxies barred like ours? That's a question nobody knows because the way that bars were explained in the past is that it's a kind of a structure that seems to form when this galaxy becomes stabilized, and bars seem to actually influence galactic evolution as well. But the actual formation is not entirely understood very well. And dark matter potentially plays a role, but it's not certain. Right now, it's one of those open questions, especially since barred galaxies have now been discovered by the James Webb. Some of them are mere hundreds of millions of years old and makes no sense. So right now it's basically uncertain how they form. Nobody knows. I'm sure it will be at some point explained, maybe in the next few decades, and hopefully because of this telescope. Right now, it's a mystery. Okay, next question. Let me see. Vesper Valentine, thank you so much for the donation. I've been watching for years and wanted to say thank you. No, thank you. Thank you for watching, because that's basically why you do this. Someone asked me what I do nowadays for work. Basically this, I'm really grateful to all the Patreon supporters and everyone on this channel. Over the years, basically ever since COVID started, I had to take a pause. Also after, we had a family tragedy a few years back. Some of you might know what it is. I took a break from teaching. I used to teach math, and I just couldn't do it anymore, just because it was too painful. And started doing this full time. So it's been 3 years now, full time YouTubing. We'll see how it goes. I might have to go back to teaching if I find a good position somewhere. Oh, thank you. Someone actually corrected me. Rubin was granted honorary doctorate from Harvard, Yale, Smith College, Grinnell College, and Princeton. That's awesome. Yeah, she definitely deserves it. I mean, she's done a lot of research that was absolutely groundbreaking. Can Rubin... Oh, what's happening? Okay, wait, hold on. Oh, here we go.
World today.
This is the first image.
Thank you for your reaction. But now that we looked at this image, I have to reveal a fun fact. This image actually shows only a small portion of one Rubin image, just about 2%. In other words, the entire Rubin image is 50 times larger than what we are seeing here on the screen. So you may wonder, why didn't we show the entire image? Let us see why. Rubin Observatory, including its Simoni survey telescope in the middle, LSST camera on the left, and an exquisite software framework, is designed to make huge images rapidly. These three components you can see on the screen and their technological breakthroughs is what makes Rubin and LSST possible. Let us first have a quick look at the super agile Simoni survey telescope in the middle. You will notice the color scheme is matching everywhere, and indeed, my official Rubin tie is modeled after the telescope. Here you can see Simoni Survey Telescope inside the observatory's dome. The point of this short video is to demonstrate the amazing ability and agility of this 300-ton telescope. No other large telescope in the world can move this fast. It moves around in seconds. Other large telescopes take minutes. Let us now look quickly at the LSST camera. This big, beautiful camera is already in the Guinness Book of Records as the largest astronomical camera ever made. It makes huge images. As we just heard, just one Rubin image covers sky area equal to 45 full moons with its 3,200 megapixels. But that many pixels makes it very hard to display such an image. This is more pixels than the human eyes, your eyes, my eyes, can see. And this is the main reason why we could not show you the entire image right away, but only this small image shown in the bottom right. You can see its relative size to the full field of view in this small rectangle at the bottom. As Director Grazios pointed out, we would need 400 high-definition televisions to properly display just one Rubin image so that your eyes could capture all the detail. That means covering a basketball court with 400 TVs to display just one image so that your eyes can see all the detail. But instead of looking at 400 TV screens or walking around a basketball court, our team has developed a powerful web display tool that we can use to move around our giant images. We can zoom in and zoom out. We can explore and admire details of any object you choose to look at. Next, we will look at a region of sky about twice as large as one Rubin image. It is centered on the giant elliptical galaxy called Messier 49. This region that we'll explore in a second is about 100 times as large as the first image we saw today. The follow video is 1 minute long, and we will first enjoy it without any comments. Then we will replay it, and I will comment. Enjoy. We will look at it again. Before we start, I want to say that the entire Rubin team is so excited about this data. We have been talking about this data for over 2 decades. It's finally here. Let's look at it again. Please pause. You can see here a universe teeming with stars and galaxies. The seemingly empty black pockets of space between stars in the night sky, when you look at it with unaided eyes, are transformed here into these glittering tapestries. There is barely a pixel in this image that doesn't have some light coming out. And only Rubin can produce quickly such large images with this much color and richness. Please continue. Play. You can see spiral galaxies, elliptical galaxies, clusters of galaxies. Please pause here. This is an amazing region. We need to stop here. I love it. Do you love it? Yes. Everybody loves it. Here you can see a stunning variety of celestial objects, from bright stars in our galaxy, ranging in colors from blue to red, to these nearby blue spiral galaxies, to more distant elliptical galaxies that are yellow and red in color. You can see how vividly these colors are, and that's very important for science. Colors of galaxies are very important because using these colors, we estimate distances to these galaxies. You can also note in this image that galaxies are not randomly distributed in it, but they are clumped. They show clumping and statistical details of that clumping, and distances to these galaxies determined from LSST colors will enable very precise, unprecedentedly precise studies of the expansion history of the universe and studies of dark matter and dark energy. That's what we measure, where these galaxies are, how big they are, and what are their colors. And in few years, LSST will be producing unprecedented cosmological results. Let's continue. And now you can see the full extent of that image. It's about 2 LSST or Rubin fields of view. And this is how we scan the sky, 30 seconds per exposure. There were about 10 million galaxies, close to 10 million in that image. Thank you. This slide shows again the whole area that we just looked at the end of video, with the first image from today outlined in the top left corner, that small portion where your eyes could tell the detail. Known objects here are annotated with their names, and you may notice that most faint objects do not have their names shown, and that's because they have not been studied before. Most of these objects have never been seen by people before. As we already discussed it, in this projection, you simply cannot see all the details in this image because our human eyes and our screens are not good enough and large enough. There is so much more in this image that you can enjoy, that you could see in that 1-minute video. And you can actually do it yourself later at home using our tool that we developed for this purpose. All you need is internet, and at the end of the presentation, I'll give you a QR code with a link. And now I'm talking to our colleagues and friends on the internet watching us through YouTube. At the end of the presentation, you will get a link, and then you can spend the rest of your day enjoying these 10 million galaxies. We hope you enjoyed it, but there is more to show you today, much more. Imagine now an image like what we just looked at, but imagine it 1,000 times larger. That would be half of the sky, or the entire sky visible from Chile. That 1,000 times larger image than this giant image we just looked at, this is LSST, Rubin's main goal for the next 10 years. But LSST will be so much more than just an image, even though such great large image, it will be so much more than just an image. And that is because every object included in LSST, about 40 billion of them, for the first time more celestial objects than living people on Earth. Every object will be imaged about 800 times during these 10 years that it will take to deliver LSST. And that brings us to the greatest movie of all time, LSST. Because we will have 800 different observations, we can take these frames, we can put them in a movie, a digital color movie of the night sky. As I said, Rubin Observatory is the greatest astronomical discovery machine ever built. So let's see quickly what makes it so uniquely powerful. Most importantly, it can scan the sky super fast, about 10 to 100 times faster than any other large telescope. This is like comparing the speed of your car to the speed of an airplane. That's what we are doing. Instead of driving around from east to west coast for many days, we pop on a plane and we are there in 5 hours. That's what we are introducing here. It took us a few nights to collect data we are showcasing today. With existing facilities before Rubin, it would have taken at least a year and maybe more. And LSST would take 1,000 years, which is obviously impractical, not 10 years. This is why we had to build Rubin Observatory. And so let's talk now a little bit about movies. We have a couple of trailers to show you. So objects, we make movies of the night sky to see two things, objects that move and objects that change brightness. So objects that move come in two flavors. Stars in our galaxy move, and they move slow. We detect it, but it's slow. Much faster objects are asteroids, and they are in our solar system. And so we'll focus now on asteroids that we discovered in those few nights of data. So here nothing is moving yet. This is just to show you a tiny portion of that image that we will zoom in to discuss asteroids. Nothing is moving here either. What you can see is two spiral galaxies. What you cannot see is that these two beautiful galaxies were photobombed by asteroids. Let us see how. Here you can see asteroids as colored streaks. They are not satellites. They are asteroids that move during exposure. And this color image is made by combining many individual exposures. But asteroids, because they move, they disappear after you got one picture of them, one exposure. So these colors correspond to the principal colors used to construct color image. So you have red, you have green, you have blue. And so these asteroids, when we combine the image, we can remove them. Our software is smart enough to recognize them and remove the streaks when combining individual images. This is why you did not see them before. But now we will focus on asteroids. It's another 1-minute video. It showcases our unprecedented ability to detect small objects orbiting the sun. You can see motion against the static background of stars and galaxies. And we are only showing asteroids discovered by Rubin, not previously known asteroids. These are all new discoveries that were reported to the Minor Planet Center at Harvard this morning. There are so many of them. Just a few nights of data, just one tiny region on the sky. And now you will see their location in solar system. Let's pause here. So this blue donut, this is simulation of all the asteroids we expect there. And because we only spent few nights to get these data and we looked towards one small region on the sky, all of these new discoveries are found in this one narrow slice of this big donut. In 2 or 3 years, after we start LSST later this year, we will sweep around and discover all of these millions of asteroids. So we had 2,000 in these few nights of data. There are 7 near-Earth objects that have orbits that cross Earth's orbit. None of them is in such position to strike Earth, don't worry. We'll get tens of thousands more near-Earth objects. And we will discover about 5 million new asteroids during the next few years with LSST. This is 5 times more than all the astronomers in the world discovered during the last 200 years since the discovery of the first asteroid. So because of this rapid development of technology today, we can outdo all these 2 centuries of effort in just a couple of years. Let us now see another illustration of the ever-changing night sky. We will look at objects that change their brightness. They don't move, but they change the way they look. We will look at stars that are called variable stars because they vary in brightness. They can change brightness on timescales from minutes to years. And by the end of LSST, we'll have data, we will know of about few 100 million variable stars. This is mind-boggling to people who work in this field. LSST will also discover a few million supernovae. Supernovae are exploding, dying stars that are very important for cosmology because it's relatively easy to estimate their distance. We will now take a detailed look at a few variable stars called RR Lyrae. They can become twice as bright in only a few minutes, half an hour. That's why we chose them for this presentation. They are in reality about 50 times more luminous than our sun. And they change brightness because the whole star is pulsating like this on time scale of some hours. They are also very useful for studying dark matter in our galaxy because we can get their distances easily too. Here you see this blue star. It's blue because it's hotter than our sun. Our sun would look yellow in this image. And here we are comparing its brightness. Please pause here. So what you can see is color image of that star, average color image, and these 2 observations show its brightness in individual images. And the one in the middle is 30% brighter than the one on your right. It is hard to tell with your eyes, but it is very easily measurable in our high-quality images with our high-quality software that goes through those images. Let's continue. We'll see a few more RR Lyrae. The next example is even harder to tell with your eyes. It's only 11%. But again, for our powerful, precise software that looks at it, we know it's 11% and not 10 or 12. All these stars are found in our home galaxy, the Milky Way. It's easy to get their distance. To distances much further than we can do today. And so over the next few years, we will map the distribution in the outskirts of our galaxy of both stars and dark matter more precisely than ever before. As you can see, the strength of Rubin and LSST is in huge images, in fast scanning of night sky, in discovery of huge samples of billions of celestial sources, and in studies of those sources with time, how they vary with time, do they move, do they change brightness? And that is the real purpose why we built Rubin Observatory. But there is one more thing to tell you today. As we look at the sky, we don't only collect huge samples, we make images of beautiful objects. And so today we want to share with you few beautiful objects, and we chose the Trifid and Lagoon nebulae. These nebulae are giant clouds of gas and dust, and they represent stellar nurseries. They are places in our galaxy where new baby stars are born by those clouds collapsing and becoming hotter and denser until you end up with a protostar, with a young star in the center. So this is the whole image. There are 2 nebulae. Top right is the Trifid Nebula. This pink nebula in the bottom is called the Lagoon Nebula. Again, this image is very large. It's about as large as the entire Rubin image. and your eyes and our screen are not good enough to display all the detail that we recorded in that region. Again, we will show through video that zooms in around all the vivid detail that is captured in that image. So, ready? Warp 1, engage. Wrong video. How did that happen? Peculiar. All right. We will have to leave that for later. So let me say a few words about what's next for us. That video, by the way, you can see when you follow the link from before, so nothing much is lost. You can enjoy it later. So we've just seen mesmerizing treasure trove of the stuff that LSST will start producing. We are getting to the close of the construction project. We are not done yet. We have some commissioning work to complete, some verification work to complete, but in a few months we expect the project to be completed. We go into operations, and we will start this greatest digital movie of the night sky later this year, and it will go for 10 years. We did not talk today much about science, but I do want to mention over 2,000 LSST scientists who are eagerly awaiting the start of LSST survey. We want to thank them today, thank them for helping us to arrive to this point with their support and expertise. They helped us first build the science case for LSST that led to LSST being ranked #1 in NAS Decadal Survey in 2010, and they also are helping us to build Rubin Observatory. They are organized in 8 topical science collaborations, and they greatly benefit from the supporting nonprofit organization called LSST Discovery Alliance. It's formerly known as LSST Corporation, and that is the organization that started this project. But I also want to emphasize it is not just the scientists who will enjoy LSST data. It is everyone with curious mind interested in what's up there. Every child in school, we will have tools and materials that our education and public outreach team produced that you can use to be citizen scientists, that you can see in videos in planetaria, that if you're a teacher in high schools, it maps on your science curriculum. All of these will be available from that link QR code in this slide. And so now I will finally finish this brief presentation. The entire Rubin team, and let me add that I was greatly honored by our Rubin team to represent us today. The entire Rubin team hopes that you enjoyed this presentation. Please stay tuned for the exciting discoveries expected from LSST over the next 10 years and beyond. Thank you all here. Thank you all who are watching us over internet. Hundreds of locations in the US and Chile. Thank you and muchas gracias. Thank you to several hundred, close to 300 other locations around the globe. Hvala svima. And thank you for being with us today. And a big thank you to SLAC and Aura, our managing organizations. Heartfelt thank to our funding agencies, NSF and DOE, to our awesome program officers, Dr. Eda Jar, Dr. Kathy Turner, thank you, thank you, thank you. And finally, we are all very grateful.
Okay, he is thanking everyone, and that's great, but also we have so many questions that we didn't get to answer. Okay, so I think that's pretty much it for their stream. Oh wait, unless there's a Q&A. Is there a Q&A? Hold on a second. Probably not. I'm going to listen with one ear. So before we finish the stream, I just wanted to go through a very, very quick Q&A from, I guess, my side, because I'm sure there are probably a lot of questions. I'll try to answer everything I can, but I cannot answer everything. Oh, wait. Oh, there's more. Oh, there's a panel. Okay. Yeah, there is a question, Q&A. All right, so I'm going to turn back their stream once they start answering the questions. One question I didn't get to answer here was someone was asking me, can this telescope see technosignatures? The answer is very likely a big no, mostly because that's not its main purpose, and technosignatures is an open field. We don't really even know what to look for. Normally, when it comes to technosignatures, researchers look for specific wavelengths of light, and you have to be able to see an actual star system and a planet. That's not the main mission for this telescope. It's mostly, think of this as a kind of a, I guess it's creating a kind of a Google Earth of the universe. So it's basically creating a massive amount of data, a map of the entire southern night skies. That's why it's probably not going to be good at detecting technosignatures. Also, there was another question, but I already forgot what it was. But during this stream, we did get to see how good it is at detecting asteroids. Within just a few hours, it was able to detect thousands of different near-Earth asteroids, and that's just mind-blowing. Like, imagine in the next year or so, we'll have like millions of asteroids to study, or at least to study their orbits, making sure that they're not dangerous, because that's really one of the main missions here. And it was really cool how they explained how it's able to see the variable stars extremely well, thus helping researchers establish distances to various objects. So when it comes to variable stars, such as Cepheid variables, which are probably the most famous ones, that's the stars that kind of like, they blink, but they blink with a pattern. Oh, wait, there's a question. 1 second, I'll be back.
To scan the entire southern sky in only a few nights with this exquisite image quality.
Thank you, Sandrine. Aaron Rudman.
Hello, I'm Aaron Rudman. I'm a professor at the SLAC National Accelerator Lab at Stanford University, and I've been honored to lead the team at SLAC that built the world's largest camera. I'm particularly excited about the discoveries that the Rubin Observatory will make, and particularly eagerly awaiting the light that we will shed on the nature of dark energy and dark matter.
Thank you. Victor Krabendam.
Good morning. My name is Victor Krabendam. I am the project manager for Rubin Observatory. I joined the project 21 years ago, but it's been my honor for the last 13 to be leading the project. The team that we represent here today is an incredible one. We have persevered, we've innovated, and we have overcome challenges. And right now, we envision that the project was going to be everything that we dreamed it would be. I look forward to delivering this project on budget and handing it over to the operations team later this calendar year. On behalf of all of the scientists, the engineers, the administrators, and the technicians, I want to thank both agencies and some early donors for trusting us with over $800 million to make this ambitious project a reality. Željko mentioned Dr. Turner and Dr. Ajar. I just want to recognize...
All right, I'm back. I thought they were asking questions because I do actually want to hear some of the answers. So this is more comments and about everyone thanking each other. I mean, it's great to hear that, but we're here for the science. Anyway, so what I was talking about? I was talking about something in regards to variable stars. That's right. So Cepheid variables are super important for establishing distances. Some stars out there, they blink. They blink with a certain pattern. They go brighter and dimmer, brighter and dimmer. And over the years, researchers established how they do it. And because of this, we can now establish distances to various distant objects if we can find those stars. That's actually how Edwin Hubble was able to establish the distance to the Andromeda Galaxy. And so this telescope apparently is one of the best for doing this now. And so it will be able to detect a lot of new Cepheid variables and other variable stars, thus allowing us to recalculate distances to various objects and potentially either resolve or the mystery of dark energy and maybe some other mysteries in regards to the expansion of the universe, or make it even worse by basically establishing that distances are actually farther or closer and so on. So anyway, it's going to be improving our universe maps in a sense. Okay, so I missed another question here somewhere. Let's see. Thank you so much for the donations, and let's see if there's a question here. Thank you, Alev. Thank you, Shapely Attractor. What does greater resolution mean for dark matter hunting? I think what this means is that basically we need to find a solution to dark matter, because nobody knows if it's a particle. Nobody knows if it's if we need to rework some of the physics, if we need to rework some of the formula, whatever. That's basically the biggest resolution. If we can actually physically find a particle, solved, done. We can close that book. But it's been decades now, lots of different experiments. There was a video I made just last week, I think, about a potential detection of maybe dark matter, but there are other explanations, and it could be a neutrino, and so on and so forth. So that's basically why this telescope is important, because by measuring the weak gravitational lensing and by measuring a lot of other parameters inside different galactic clusters, it will actually help us figure out maybe what it is. Right now, it's an interesting question to answer, because a lot of physical concepts kind of depend on it. The entire cosmological model depends on the dark matter principle. So if it's not real, then everything has to be reworked again. Next question. Robert, thank you so much for the donation. And can it find Planet 9? That's one of the missions. Hopefully, within a year of operation, it will capture enough of the southern skies to see if it's in the southern skies or not. It will be able to detect very minute motions of tiny objects. And so if it does see a very small object moving super slow on the outskirts of the solar system, we'll know for sure that it's Planet 9 or not, but only the southern skies, because it could be in the northern skies. So that's the little shortcoming there. Aris, thank you so much for the donation. And the question is, oh wait, where did it go? This is only the beginning. We will get full 4D exploration capabilities for every user in this vast library of real-time recorded data. Oh, that's a question. Will we get full 4D exploration capabilities for every user in this vast library of real-time recorded data? Oh, okay, I see what you're asking. We'll be able to explore the data of the telescope. Well, just like SDSS, which is the previous survey that was able to collect a lot of data on different stars, this telescope in the next few years will collect enough data where you'll actually have like a website where you can just go in and you'll see all the stars there. You can even do this right now for SDSS survey. There's a map you can access. Sloan Digital Sky Survey is the name of this one. But do I have the link? I don't have the link. Here, let's go to the classic one. Anyway, it's definitely going to have a website like Access service, which is probably going to be available by possibly 2026, I guess. Anyway, I'll post the link for SDSS later once I find it. So yes, the answer is yes. Will it be stored in analog memory systems providing larger storage? That, I don't know, I'm sorry. I don't know where they're going to store it. Next question or concern. Will this add, oh, thank you so much, Team Alaska. Will this add to our ability to see the creation of planets? Not really. So for planetary creation, you need telescopes that can see through dust, because normally typical young star systems, which we sometimes refer to as propylids, which, funny word, you might want to look for this in one of the links in the description. I'll post it later. It's essentially, it's like a cocoon of dust. And to see planetary formation, you have to see through that. And you need to have either radio or microwave telescopes for that. So for that purpose, you need there's another telescope that's also in Chile. It's called ALMA. And that one does a pretty good job. It can see planetary formation. But it's not super high resolution, though. So we still have a lot of shortcomings there. Okay. Cool. Can it see UFOs? I don't know. Can anyone see UFOs? I don't know. Not a UFO channel, to be honest. It's evidence-based only. Okay. What's this? Thank you so much, Suhoi29K. Would Space Engine implement all of this 10 terabyte data? So a Space Engine is the simulation I sometimes use for visualization of different planets and stars and so on. It already has all of those objects in there. there's no need to have the data from this particular telescope, because here, what this is going to be doing is basically introducing new asteroids. Oh yeah, okay. It will probably have new asteroids, and it will probably be introducing much more accurate maps and distances, and much more accurate gravitational lensing effects that we can now measure. So this is more for accuracy as opposed to actual objects. And Space Engine is, I think there's only like 2 volunteers doing most of the work, so I doubt they'll have time to introduce everything in there. It's pretty hard. I mean, I actually, long time ago, when this channel just started, I tried to do a lot of different Space Engine mods and so on, and it was super challenging. It's tough work. Even putting all this data in to like new planets, new stars, and so on, it takes a lot of work. So I'm actually grateful that they do as much as they do. Next, what did I miss? Oh, wait, I'm not listening to what they're saying.
Data this will create and how NSF and DOE have approached making that available to researchers quickly through the science platform and alert system. And then my follow-up would be what the timeline for those tools are going forward.
Oh, let's listen to the answer. I don't know what the question is. I missed the question, sorry.
So with all the data, I think you get a sense from Željko's presentation how much data we're talking about. As he said, about 10 to 20 terabytes of data every night. Very early on, people realized instead of sending the data and the software out to scientists, it's much better to bring the scientists to the data. And so there's something called the Rubin Science Platform people work very hard on, where you can actually just log in to the cloud and have access to all of the data, be able to do queries, analysis, and so on. And you know, it just works. It's fantastic. Rather than having to distribute software, you just have it all there set up for you. So that is something that is, you know, I think we're very excited about. The timeline, we have a sequence of data previews from the commissioning data. In fact, the first preview using the ComCam data is about to hit the streets, and then that will be followed by a second data preview from commissioning, and then release of the data through a regular data release schedule that's known to the community.
Can I just add, Željko?
Please do.
And also, so Steve has really outlined how science community can get access to the data, but there's also opportunities for the public, for anyone to participate in this discovery process through citizen science. So our partners as Universe will be hosting citizen science projects that anyone in the world can help us sort through this amazing treasure trove and create those projects. And so, as Steve mentioned, the first data is coming with that was taken with the commissioning camera, and so we'll have our very first small projects coming in the next couple of months that are all kind of building up the foundations and the frameworks and the resources for the launch of the survey and all the projects that will come after that.
Fred, do you want to add a few words?
Yes, let me add on top to that, we also, as you mentioned, we also have the alerts. You've seen how Rubin will build this cosmic movie. We have things we're looking for, we're trying to understand things that change over time. So that particular data product will come through in the form of alerts. So overnight, our data runs really fast from the mountaintop all the way to Slack, where it gets processed. And we look at what changed in the night sky compared to how we know that the sky looks normally. It looked before when we looked at it earlier. And then every time that something changes sufficiently that we can detect it, technically at a 5 sigma level, we package that into an alert packet. So we collect the information about it, where it is, how much the brightness changed, how much the color changed, and we add postage stamps of that part of the image that scientists can use to do their science, of course, but also to trigger other facilities that can take more data about those things so we can learn about them even better. And those get distributed worldwide. That particular data product has no proprietary restriction because we need all of the scientists in the world to point their telescope to learn more about these things that we discover.
Thanks, Fred. Mike, back to you.
Hi, Mackenzie Perlman from Science News. And thank you all so much for having this press conference today. Going off something said just a few moments ago, you even talked about the citizen science projects being starting, and you've clearly made this all very accessible to the public through your Skyviewer app and other ways. Can you talk about the importance of bringing the public along throughout this journey and over the next 10 years?
Thank you. I'd love to talk about that. So this is an amazing data set, but it's also a very complex data set. And so one of the things that our team that has been part of the observatory since the beginning has been working toward is making many ways for people to engage with this data in whatever form you would like, whether it's just enjoying beautiful images or looking on social media, or we have an educational component, and so we're bringing Rubin data into the classrooms. And one of the things I'm really excited about is the fact that we're about to see a generation of students who will can see Rubin data in their classrooms in high school, and then perhaps choose to study that in university, and then go on to maybe make the next amazing discovery that will be in that treasure trove of data that is produced through the survey. And so we have many options like that. One of the other things that's in there is we also have a way to explore the data through sound and sonification. And so that's also part of our Skyviewer app that is just as what you're seeing visually is mapping that color data into a visual landscape. We have a soundscape that also is the same representation of that data that you can explore.
As a reminder, there will be more than one star and more than one galaxy for every living person on Earth. Thank you.
Hi, Sam again from AFP. I have another follow-up on the asteroid detection capabilities. Earlier this year, we had 2024 YL4, a city killer asteroid, which briefly posed a risk to Earth. How will Vera Rubin Observatory help in these detections? Will we get more lead time? What do you expect to see out of the asteroid hunting and the planetary defense capabilities? Thank you.
I can take that question. So, solar system science is one of the 4 scientific pillars of Rubin. So we have developed software framework that can fully utilize our images to make unprecedented discoveries. We are not particularly designed for near-Earth objects, but because we look at everything, we will be extremely efficient at discovering near-Earth objects. And as soon as we have a plausible discovery, all our data will be on daily basis sent to the Minor Planet Center at Harvard, which is the world's clearinghouse for these observations. And sometimes even within less than 24 hours, everyone in the world will know that there is a potential object that could be hazardous, and they can get more data. In practice, typically, once you get more data, you rule out the level of the danger. But you need more data. Everyone in the world will be able to follow up on Rubin's initial discoveries. Very often we'll get our own orbits too. I'm Željko Ivezić, and you can spell it the way I pronounce it.
And your role?
Thank you. I think it's time we gave our journalists online a chance now. So our next question is from James Deenan at New Scientist. What are the unique capabilities of the telescope that enable it to detect so many more asteroids than other instruments? Are these early detections of so many asteroids unexpected, or did we expect this volume of objects? How many Rubin detections will feed into existing planetary defense networks?
They were not surprises. We have exquisite simulations that we used, for example, to predict we'll discover 5 million new asteroids. Can you repeat the first part of the question again? Just the first part.
What are the unique capabilities of the telescope that enable it to?
So that is interesting point. So when you ask for each of our 4 science pillars, which vary a lot, from asteroids in solar system to cosmology to dark energy and dark matter, when you ask what kind of system would you like to have, and we asked that question 20 years ago, you get very similar answers. And that's another power of Rubin Observatory that we didn't emphasize today, that we get one data set that will serve all these different science goals. We do not get specialized data for asteroids, specialized data for dark energy. It's one and the same data set because observatory is designed to be so powerful that we can get such a powerful data set called LSST, which will serve everyone. That's why we can get so many asteroids. The short answer is you need to scan the sky very fast with very large field of view, repeatedly for a long time, and that's what we do for every science program.
All right, thank you. Our next question is from Katarina Miller from the New York Times. She asks that, given the length of time it took to bring this project to fruition, how does it feel that the observatory is complete?
I will call on Sandrine.
It's great. It's really an amazing achievement. It's the achievement of, again, I mentioned 10 years of work of a lot of people, really carefully and methodically putting everything together, designing properly, using the best technology to align the telescope, to build the camera, and build the data pipeline behind it. It's really the results of a lot of very, very careful and hard work. So that's why it feels great.
Thanks, Sandrine.
So Katarina had a follow-up, and that is, now that the first look milestone is complete, what can we expect next from Rubin Observatory, particularly between now and the start of the survey?
I think that's a question for Victor.
So we are completing the construction project, and what we are looking forward to is finishing up the validation of the observatory and how it functions, tuning it up to make it work exquisitely and continuously. And so for the next 3 or 4 months, that'll be our main objective. And after that, we'll be handing it over to the operations team.
Thanks, Victor.
Great. Our next question is from Megan Bartles of Scientific American. She asked, I know it's challenging given the size of the images, but could a few of you point out something that strikes you as particularly interesting when one of you looks at these images? Essentially, help a non-scientist look at this part of the data the way you do.
So if you look at the image where we had spiral galaxies and you had also clustered galaxies that were more yellowish in color, that tells you how far they are. And when we look at two-dimensional images, all the objects that are different distances, they are projected into one plane. But with the power of this data, the power of recorded information that we decipher with our software pipelines, this projection of 2D image becomes three-dimensional data. We unpack all these objects into three-dimensional distribution. That's what I find exciting about this data. It gives you the third dimension that without this data you just don't get. It's like looking at constellations. Constellations don't have the shapes in reality. These stars are different distances, but they project to us to bears and lions and everything else. Once you have the third dimension, then you realize, oh, that looks totally different. And that's what we want to know with galaxies too, to do cosmology. Aaron.
One thing I would like to add to that is when I look at the images, I often don't pay attention to the beautiful nearby galaxies. I look at the little fuzz balls. And if you zoom in close to any one of our images and in almost any portion of the sky, you will see tiny little galaxies. To the eye, they look like small balls of fuzz. But many of those galaxies are 5 or perhaps even 10 billion light years away and have up to 100 billion stars in them. And those are the galaxies, actually, that we use the most if we want to study the expansion of the universe and dark energy.
Thank you, Aaron. Steve, you want to add a few words?
Yeah, we thought a lot about how to select targets and how to represent images. And I think what we hope as people engage and look at these images, first, I think we hope you see them as beautiful. And they're also a little different from what you're used to seeing, actually significantly different. The difference I would point out, and what we're so excited about, Joko said it, but between objects in most astronomical pictures, it kind of looks like inky black space. That's what you've seen before. But that's not what you saw here. What you saw was that inky black space actually is full of stuff. It's full of galaxies. It's full of all kinds of interesting things. And it's because of Rubin's unique combination of capabilities that we're able to bring that all out and to see it and do the kind of fundamental and broad range of science that Aaron mentioned. And so I hope people just see that and the vast range of colors and vast range of different kinds of objects that we are going to see. In addition, there's all the time domain stuff that you've already heard about. And I think the thing we hope everybody sees also is promise and opportunity to find the new stuff that is just, waiting for us. And so I think it's that combination of things that we're really most excited about. And we hope people will take the time to really explore these images because, as I said, they're different. And it's the reason that the EPO team built the Sky Viewer so that you can have a look around. And we hope people enjoy that.
Thank you, Steve. Mike?
All right, our next question is from Greg Redford, the space reporter at WTOP News here in Washington, D.C. He asks, what is the most anticipated discovery made by LSST? What surprises await?
So there are so many of them, it's hard to pick one. We will be looking for unknown unknowns, but we also know that some of the discoveries will be made. I already mentioned earlier today 5 million asteroids, and not everything will be discovery. We are also doing precise measurements in cosmology, in dark matter, dark energy context. We'll be measuring things precisely. That's one of the goals. We will get some unexpected discoveries, like, for example, interstellar objects that we are now in position to get 10 or 15 of them and get much better understanding than those two that are known, Oumuamua and Borisov. So we will learn a lot. Of course, every survey prior to Rubin and LSST, every big project that scanned the sky discovered many unexpected things. So by that argument, we think we'll discover a lot. But then different people are excited about different things. Maybe Fed can tell us in the time domain context, what are you excited about?
Well, I'm going to double down on the unknown unknowns. And I love the question because can you tell us what the surprise is? No, it's a surprise. That's a bit tautological. And it's really exciting that it is a surprise. And I want to emphasize how difficult it still is going to be to find those things that we have never seen before. People make the analogy, it's like a needle in a haystack. It's not. It's a needle in a haystack if you don't know what the shape of the needle is, if you don't know what the color of the needle is, if you don't know whether the needle moves through the haystack, and if you don't know really what the haystack is composed of, because there's millions of things in the haystack. We don't know all of them to the same level of detail. So it's really an adventurous horizon. And yeah, I'm very glad that we cannot answer the question what surprises there are going to be, because they're really surprises.
All right, great. Our next question is from Corey Powell from American Scientist. He asked, how will Rubin be able to expand our understanding of the far outer solar system, deeper into the Kuiper Belt and searching for interstellar objects or even Planet 9?
Yes, all of the above. If Planet 9 exists, it is still just theoretical conjecture. If it exists, Rubin is the best positioned observatory to discover it. We will also obtain very sensitive images very quickly over a large area of the sky, including the full ecliptic coverage, the plane in which these objects move. So we will extend the outer reaches of solar system by a large factor. We will see way beyond the orbits where Pluto and other Kuiper Belt objects are found. We will be sensitive, it depends on the object size, But we could see Pluto even if it were at 10 times larger distance, roughly speaking. And then for interstellar objects, so far there were 2 discovered, so it is very hard to predict how many we would discover because we don't understand population, it's only 2 objects. But by simple scaling arguments, we do expect 10, maybe 20, somewhere there. So we will be extremely powerful solar system survey.
Thank you. Our next question is from Jenna Ahart from Quanta Magazine. Is there an estimate for how many stars or galaxies are in the first image presented today? How does this compare to the full set of galaxies Rubin will observe?
I think Steve knows all the numbers.
We're still counting, but it's, as Joko said, around 10 million objects. And as Joko also said, we're expecting about 20 billion galaxies and after the 10-year survey, and about 18 billion or so individual stars. That's a lot. When you view them 800 times, that means 32 trillion or 30 trillion observations. Very impressive. And so we're really just getting started. The image you saw of the Virgo field, kind of the impression you'll have for the whole sky after about half the survey, 5 years, just to give you a sense. It's very roughly. And we'll just be able to see objects dimmer and dimmer over time. That's one of the real advantages of continuing to do the survey, to look for new things, but also to measure more precisely Aaron's fuzzy things as well. Does that answer the question?
I think so.
Very good.
Our next question is from Kobe Brown from Astro Kobe's YouTube channel. What are some short-lived or previously unseen phenomena that Rubin Observatory might uncover thanks to its rapid, high-cadence imaging?
Do you want to take this one, Fed?
Again, they're previously unseen and unknown, so no, I cannot answer this question. I can answer that we really do believe we will discover new things.
Can I add? One of the things I like to think about is the fact that when you're talking on a survey where everything's in the scale of billions, these 1 in a million events aren't that rare anymore. You get lots of 1 in a million events if you're talking on the scale of billions.
All right, thank you. Our next question is from Alana Schadwinkel from Der Spiegel. I had a look at the Skyviewer app and wondered, is the idea that anyone can discover something in this image that no astronomer has found yet? If so, how could one know if something is truly new? And what does someone actually need? What kind of knowledge or tools to be able to find something new in these images?
Claire, would you like to comment?
Yeah, so that is one of the things I think is very fun, is if you zoom in and you look at one of the little fuzzy galaxies in there, you might be the first person to be paying attention to that fuzzy blob. Someone might have glanced at it before, but you can choose your favorite in there, which is very cool. If you, using that app, you can find the position, which is given in RA and DEC, which are our coordinates, and you can look at other catalogs online that would, if there's information about that, they'll be in there. But there'll be a lot of things in there for which there is no name, there is no catalog yet until all the amazing science of Rubin comes out.
Steve, would you like to add?
Yeah, let me just add one other. There's so many great things about Skyviewer, but one of the really cool things, if you discover a scene you like or an object you like, you can zoom in to it, frame it how you like, and then the button on the lower left will give you a URL, something you can paste into any browser and share it with your friends, and they will see the same scene. So you can, that's so much better than saying, oh, you know that big elliptical galaxy sort of off to the left, go down a little bit there and then a little bit over, or try to read the RA and DEC, which you can also show or turn on and off. There are lines of constant RA and DEC. It's so much easier just to use this fantastic URL generator, and we're hoping people just, share their favorites.
Thank you, Steve. Mike?
So I think that's all the time we have for questions today. This will be the last question.
Yeah, I just perked up when you talked about Oumuamua. Do you think you'd be able to resolve the question of its origin, if it's artificial or natural, by pointing at it where you think it is now, or we know it is now?
I'm sorry, can you repeat?
Oumuamua, do you think you'll be able to resolve its artificial or natural origin based by pointing at it now?
Oumuamua is long gone. We cannot detect it, but we think we will learn more about that interesting question because we will have a much larger sample. We will get between 10 and 20, maybe even more, and then by studying statistical properties of those objects, we can ask, is it more consistent with some natural population, or we can go to far-fetched theories too.
If it comes back.
Thank you again.
Okay, so that was pretty funny, I thought. I actually laughed out loud. So the Oumuamua question was that it's long gone, and if it comes back, we know that it's artificial. That's actually a pretty good answer. Oh, I can also take off my super uncomfortable headphones. All right, so I think, what time is it? 1:30 a.m. Oh my God, I gotta go to bed. So 20 more minutes, maybe, max. Ask last minute questions. Anything else that was confusing or you didn't understand? I'll try my best to explain. But as I mentioned in the comments in the chat, I will most likely do a kind of a brief overview of what they discussed in some of the future videos, because they did mention a lot of different links that they posted and a lot of different QR codes and so on and so forth. And because their website actually crashed in the middle, it's kind of difficult to access everything. So we'll definitely come back and talk more about this. But honestly, I'm just generally more excited to see what the future images are going to be. And we'll definitely discuss some of the first discoveries from Vera Rubin in hopefully the next month or so. Cool. So we got the Oumuamua question answered. So it's long gone, and if it comes back, we know it's aliens. And if it doesn't come back, then as they mentioned in the press in the stream, they expect at least 20 different objects at least. Did he say per year? I think he said per year. Different interstellar object per year, or was it in total? No, I think it's per year. That's how extremely accurate Vera Rubin is going to be, and that's actually mind-blowing when you think about it. Being able to detect so many interstellar objects. We're not talking about comets. We're not talking about Oort cloud objects or Kuiper belt objects. We're talking about actual objects from other star systems. So here the expectation is that this telescope is sensitive enough to be able to detect practically a handful every year. So that's amazing. So anyway, so people are asking me about the next stream. Last year, when we had a stream in regards to the solar eclipse, that was actually quite amazing. I promised a stream in the next month, so I'm going to do the same this time, which means that it's probably going to be next year. It's not okay. So, truth be told, I would love to do more streams, and I know that streams are fun and this is great for everyone. The thing is, because I do post daily videos, and I have to pick up my kids in the morning, it's difficult. It's very difficult to do streams more frequently than, I guess, what I'm doing now. But I'll try to do a few, at least maybe in the next few months. Assuming there's something to talk about, because I mean, having a stream without a topic is difficult. Here we have a great topic. It's a great discussion, and definitely something to look forward to. Okay, I guess they're done with their stream. I can close this, and let's take a look at. Oh, I finally found the map I was mentioning in some of the previous comments. That's the map of different Rubin parties. Basically, every location you see here, they had either a in-person party or a virtual party you could attend to listen to this announcement and to talk about the discoveries from Vera Rubin. Anyway, we won't be needing this anymore because that's done, and I wanted to leave it on this image right here. Cool. So let me see. Let me read some of the comments I missed. Will this telescope? What? I missed the comment. I'm so sorry. So my apologies for being super slow. I need to wear glasses to read these comments, and also there are a lot of comments, and some of them are some of them have a lot of questions. So I have to be able to focus at the same time as I try to think. So Night Post is asking, what will you do with the data app images? Will you go in and discover yourself, get your name on another object? Oh yeah, so I was actually, so some of you might not know, but there's an astronomer in Canada that decided to name an asteroid after me. I was just as surprised as you, and I had no idea he was doing it. So now there's a little asteroid out there that's probably going to be visible to Vera Rubin telescope that is named Anton Petrov, and that was just as shocking to me as you. Anywho. So some people are talking about the streams. Yeah, so when it comes to streaming, I actually have done streams with Fraser Kane. And the biggest issue for me with streaming with other people, with other content creators, is that I live in East Asia, and most of them live in North America. So when they can stream, which is usually around noon, maybe 2 p.m., it's my bad time. And I basically just cannot handle it. It's very tough with young kids especially. So when I can do it, they're sleeping, and when they can do it, I'm sleeping. So that's the issue. I would love to do it with Asian streamers, but unfortunately, astronomy is not really a big field in East Asia. Even though there are a lot of there's a lot of research coming out of China, but just not a lot of streamers, not a lot of people interested in astronomy here. It's not a field that people pursue usually. Anyway, moving on. So someone's asking me, don't I want to try some educational series, basic of astronomy? I actually used to make those videos before. Like the actual channel started as an educational channel. I was teaching math and different sciences. And I did have a plan for several videos, and it's still being worked on. And I will definitely finish it probably in the next year or so. However, the challenge there is that I basically had to rely on AI tools to create the actual website for it, and it's so badly made that I'm not able to I cannot do it. It's those websites are required for basically practicing things or figuring out how to, for example, tracking different asteroids and learning how to discover asteroids. I had a whole series of astronomy videos that I wanted to create with actual practice tests or practice tools, and unfortunately AI really screwed it up for me. So it's being worked on in the future. Once I have enough time, maybe I'll take a summer break or something and work on it. But yeah, educational series are definitely coming. I mean, the point of this channel is really, it's not just entertainment, it's really education, and it's inspiring people to not forget that science exists and that astronomy is real and biology is there, and there's so many things discovered every single day that it's worth pursuing. Cool. So someone is asking me, can I just move to a new location? I would love to, but because it's really because of my family situation right now. My wife, who is Korean, she needs to stay in South Korea for at least a few more years, and we have young kids that basically they're difficult to raise without grandparents, and so we need their help. And once they get older, then yeah, definitely. But for now, I'm here. Just have to stay here mostly because of the kids and the family. And yeah, Fraser Kane is actually he's a great guy. I did 2 streams with him at least, and I would love to do more, but I wanted him to come here. I invited him a few times, but he never came. I mean, traveling from North America to Asia is a little bit challenging. Okay, so what else did I miss? Will we be able to find and track rogue planets? So when it comes to rogue planets, most of the rogue planets are usually discovered through the gravitational lensing effects. And even though technically this telescope can do it, because based on what they've provided us, what they've told us so far, there seems to be like a 3 to 4 day difference. I don't think it will be accurate enough. There are better telescopes for this, but it will be definitely able to detect some rogue planets. Actually, no, I think it will be actually pretty good at it, now that I'm thinking about it. Because it's able to detect most of the objects in the galaxy, it should be able to detect sudden changes in brightness. Yeah, sorry, my bad. Yeah, it will definitely be good. I had to rethink about it for a second. I'm like, wait a second, what am I talking about? It's really good at detecting gravitational lensing. Yeah, so it should be good at detecting rogue planets. One issue that you might have, though, is there will be definitely a time limit. So we have about 3 days between frames. So you'll have one frame, you'll have another frame, you'll have another frame, and there's like 3 days between them. So the actual gravitational lensing will be most likely not very accurate. So you'll have to use other telescopes for this. But yeah, I think rogue planets, basically anything in the Milky Way, it'll be able to detect, as far as we know, except for black holes. Black holes usually visible in different frequencies. Cool. Okay, solar and night. Thank you so much again. What's it called? Life during the next major eclipse. Date. Next major eclipse. When is the next major eclipse? It's like in a couple of years, no? Hold on, let me check. 2027, I think. Next solar eclipse. I thought it was 2027. And it's like somewhere in the Pacific, I think. No, that's not the one. Okay, so there's a partial solar eclipse in September, but that's a partial. We don't want partial. We want the total solar eclipse. Oh, okay, Greenland, Iceland, and Spain, August of 2026. All right, yeah, that's next year. That's exactly a year from now. So I will definitely stream that. I mean, if I can make it to Greenland or Iceland or Spain, that would be great. But chances are probably not, unless I can take my kids with me. Okay, someone is asking me, would I come back to Canada? Yeah, I would love to come to Canada. The issue is that, so my life has been kind of paused because of COVID at first. I used to work here as a teacher, then COVID started, I took a pause, then we had a family tragedy, unfortunately. And so we decided to stay here in Korea for a little bit. And Canada is basically my home, and it's my next destination, hopefully. But when I'm going to come back is obviously unknown. And since we have young kids now, it's just a little bit difficult to travel with them. Our youngest daughter is 2 years old, and you don't want to sit on an airplane with her for more than 2 hours. She goes crazy. Okay, cool. What did I miss? Thank you so much, Drop Barracuda, and thank you for enjoying astronomy. Some people are saying that I look good with glasses. This is a requirement. I cannot read comments or anything on my screen unless I have them. When I record videos, I actually had to remove these because they have a bit of a glare. And because of the green screen, it sometimes makes my eyes invisible. So I had to remove them. But I basically, so one of the reasons my videos might sound different from how I talk right now is actually because I don't have a script. I kind of have a bunch of points I want to make, and I think about them for a while, and then I talk about them, and I stop, I pause, I think. So that's why some of the videos are a little bit disjointed. I guess if I do find glasses that don't create glare, I can maybe have scripts and read through, from them. But yeah, it's a YouTuber thing. It's a challenge. Cool. Moving on. Anyway, any questions about the Vera Rubin telescope? Okay, so here's one. Colin Whitehead asks, will this telescope help us accurately figure out how many stars are in the Milky Way? That's a good question, but I don't think so, because Gaia telescope would be much better at that. And it has already showed us quite a lot of different stars. And also, this particular telescope, it'll be able to see stars, but I don't think it'll be better at seeing just stars. I mean, I need to think about this, though. And also, the stars that are blocked by the actual center of the galaxy, the central molecular zone, as we call it, they're still going to be invisible. This telescope is entirely optical in nature, so it's kind of like seeing things with your eyes, just like more accurately, So I'm gonna say no to that, because I don't think it will be seeing more stars. We've already seen plenty of stars in the galaxy. It will just be able to see what it can see better is changes in those stars. So if those stars are basically flaring, or if they're changing their brightness just a little bit, if they're variable stars, you'll be able to detect that for sure. So in that sense, it will be able to, like, for example, if it's a Cepheid variable, which is a star that allows us to determine distances, it will be able to see that star and then tell us how far away it is much more accurately. That will be its sort of strength, I guess. Cool. Oh, I missed the comment. Night Post, thank you so much. One day I hope to hear you say it's aliens. First of all, I have to. For years, people complain how I pronounce aliens, and I'm not changing that, by the way. But if that never happens, it was wonderful to just stay curious. Yeah. So most of you probably don't know, but my background is not astronomy. My background is actually in microbiology and biochemistry, and because of this, I still have trouble believing in existence of extraterrestrial life in general, not even aliens. Knowing what I know about microbiology, and which I'll discuss in some of the future videos, I don't think life is that easy to create, to form on other planets. I think we just, for some reason, our planet got super lucky. That's the question we cannot answer yet. But yeah, I hope so too. I hope one day it'll be like, hey, look at that, we finally found them. Aliens somewhere out there. Someone is asking me about K-pop. I know nothing about K-pop. I'm sorry. I do not expect me to know anything. Someone's asking me if oh no, my chat, where did it go? I'm sorry, my browser just crashed. Okay, here we go. I missed a bunch of comments. Is there no life on Europa? Well, this is all pure guesswork on my part. No evidence whatsoever in terms of if there's anything or not. If there is anything on Europa, on Titan, on Ganymede, even on Mars, in my opinion, it might have come from Earth. It might have been a contamination from an asteroid, from previous missions. It might have been made here, transferred there. That's basically panspermia. That's my opinion. We just don't have any evidence of anything existing anywhere out there. Right now, it's all guesswork. If, however, we discover something on an object out there, for example, Europa, right? If we actually do find something that's entirely different in structure, the genome is different, like just impossible to create on Earth, then, okay, yeah, we found alien life. I was wrong. It can be created somewhere else in different conditions. But as it is right now, just based on the complexity of biochemical reactions, how DNA is formed, how the cells are structured, just even the process of protein folding itself, it is just so astronomically difficult to create that somewhere else. And if it does exist, it exists somewhere super far away, like not in our galaxy. I think that's my sort of 2 cents. What do I think about quantum nature of tardigrades? I don't think much about quantum nature of tardigrades. I didn't mention that there was a study like a few years ago where they tried to quantum entangle tardigrades, but a lot of people also a lot of scientists kind of pushed back on that particular study because nobody was certain that was a quantum entanglement of tardigrades. On the other hand, there's also a study / hypothesis by famous Roger Penrose that maybe, just maybe, our consciousness is actually based on quantum entanglement. There's a video in the description. You can not in the description, sorry, on the channel. You can look up quantum consciousness. It's one of the videos I made a few years ago because that was a pretty interesting proposition that maybe, for all we know, our consciousness is based on quantum effects, and there seems to be evidence that something quantum is going on inside our brain, but right now nobody knows. All of these questions about consciousness, alien life, basically quantum stuff in general usually is, right now we're still kind of figuring out. There's no concrete evidence, no concrete conclusions yet. Okay, another question about panspermia. What if complex life only formed because panspermia brought alien life to an already inhabited Earth and allowed greater genetic mutation than otherwise available? Well, I mean, it's a good question, but by that logic, so okay, well, where did that life come from, right? And did it start somewhere else? And did that come from somewhere else too? Is this like a continuous panspermia? Because it's an interesting proposition, but right now there is just no evidence for either panspermia. We have not discovered any asteroid that seems to contain any life or signs of life in it. There's no evidence for life on other moons, other planets, other asteroids, nowhere out there. And there's definitely no life, even on Mars, so far at least. The most famous announcement was was the press release by Bill Clinton in 1997. That's actually when I started doing a lot of astrobiology as well as a hobby. And his announcement was incorrect. He basically jumped the gun there. There was the little. Let me show you what I'm talking about. The little asteroid that he was talking about. Allen Hills 84001, the famous asteroid. Let me see if I can show this to you by pressing. Oh, here, by removing my face. Here we go. It was this little thing. This was the biggest announcement in history of science, I guess, on the potential discovery of alien life on another planet. And later on, it was confirmed to be not life almost 100% because researchers were able to recreate this using just chemical reactions, and it was too small to be anything living, and it was like in nanometers in size. And I mean, after this, a lot of scientists became super skeptical because it was such a big announcement, and it created a lot of buzz over nothing. Because within months, someone was able to recreate this just by using chemistry. And so, I don't think it's going to be easy to prove existence of extraterrestrial life. Okay, what does the observatory do during daytime? Oh, that's a good question. I mean, the observatory itself probably just recalibrates. They probably clean it and stuff. But researchers work 24/7 for as much as the observatory is available to them. Normally. From what I know from some of the other observatories, during daytime, they actually do a lot of maintenance and data transfers. And during nighttime is when they do the actual captures, the data captures. At least that's what I know from previous observatories. This one, I'm not sure. Oh, that's a good question. Scott Brown asks, where is the line between being a rightly deeply skeptical scientist and being a scientist that rejects new data because it conflicts with their life's work, personal beliefs? That's a great question. And it's a question I think a lot of scientists do deal with every day, probably. I mean, it's a matter of, it's my ego and I want to be proven correct versus here's the data that shows something that's completely different, right? And the beauty of science is that, I mean, if you have an overwhelming evidence coming toward you, you just have to accept it. You know, suck it up and be the man, be a big boy and just accept it. And it happened to most scientists, I think. Not all scientists. There are actually still scientists, even alive today, that in the 60s proposed that the Big Bang Theory was incorrect, and they still refuse to accept it. And though I understand their point, the evidence is just completely overwhelming against them, and it's the so-called steady state theory does not seem to align with the data we have. Yet they refuse to accept it because they strongly believe that it's not true. And in that sense, well, you can still hear their opinion. I mean, that's also the other beauty of science, is that you're still welcome to accept someone's opinion, but if the evidence is against it, I think it's fair to say that they might be incorrect, and that's just something that is great about science, is that it's a sharing of opinions, but the evidence always wins. Someone has asked me if I'm religious. Once upon a time, a long time ago, especially when my mom passed away, I became religious for a little bit to deal with my number one tragedy, and unfortunately it didn't work, and so not anymore. I'm religious in the sense that I'm just as religious as Einstein. He once said that he believed in the God of, what's his name? The God of, I have to look it up real quick. God of, he believed in God of Spinoza's God. It's named after Baruch Spinoza, was it Dutch? Was it a Dutch or Spanish philosopher who basically proposed that, the universe is the God. So it doesn't have to be conscious. It doesn't have to be thinking or caring about us. It's just there. It's something that's there. And in that sense, yeah, I think there might be something, but it's just you believe in the universe as a thing. And that's what Einstein believed. And that's kind of what I think is maybe out there too, but beliefs are, to me, they're not important anymore. In my opinion, it's more important to follow the evidence, and if there's an overwhelming evidence for something, you really have to kind of accept that you might have been wrong. And I've taught myself that over the years. I was wrong about a lot of things in some of the previous videos even, you just have to find a way to accept that sometimes you're incorrect. So that's the answer. Maybe not a good answer. Okay, so I'm trying to see some questions. If there's any last questions. I'm probably going to stop this in about 5 minutes, but mostly because it's 2 a.m. here. So someone is asking me if I believe we will live inside a black hole. So in the last few years, there's been a few studies about this. They're mostly on sort of circumstantial evidence. I wouldn't say it's very strong evidence, but evidence in regards to things rotating in a certain way, and possibly some explanations in regards to how we have a horizon that seems to resemble a black hole horizon, except that it's on the outside. What was the other evidence? Anyway, a long story short is that because there are other better explanations, and because the black hole explanation is really more of a hype explanation as opposed to okay, that makes sense. Right now, I don't think so. It really does not look like we are inside a black hole, especially based on some of the studies we have. Like for example, the rotation studies, they've established that it seems to be a bias, and there seems to be something going on, but it's not entirely certain if the things are rotating really how we think they're rotating, or if it's just we're seeing them rotate this way. As a matter of fact, a lot of studies established that things just seem to clump a certain way, and that's because of the so-called cosmic web, which kind of resembles this humongous web of stuff across the universe. Kind of looks like this. And because of this, things just tend to organize a little bit differently around the universe. And this might give us a bit of a bias. So it looks like, things are rotating this way, but it's really because they're just kind of in the same location. So right now there's just not enough evidence about the black hole, living inside the black hole hypothesis. It would be cool, obviously. And there was a recent study that tried to explain this as basically the universe, the Big Bang, was a kind of an expansion of the black hole as a result of some kind of a entropy effect. It was a very difficult explanation. It took me a few hours to even wrap my head around it. But having read through the study and having read some of the counter evidence, it's like a cool proposition. It kind of makes sense, but there's just no evidence that they're correct. Mostly because we don't have enough evidence from before the Big Bang. We have no evidence for what happened in the first few nanoseconds of the universe. And so what they're saying is okay, it's cool, it explains some stuff, but it just doesn't explain enough. So I would say no, at least for now. Maybe they're right, but for now I would say that we seem to be in a universe that's just expanding. I don't think there's anything more to it for now, at least. So anyway, let's see if I missed anything important. Okay, I need my coffee. Could it be a white hole? So as of 2025, what is it, almost July 2025, from all of the observations out there has not been a single white hole discovered anywhere in the universe. And so I don't think it's a white hole. I think white holes might be just hypothetical or may exist in some kind of a reverse universe that goes back in time, but we don't seem to have white holes. Sorry. Draw Barracuda is asking me a question I deserve right now because I'm so tired. Do I ever imagine myself as a giraffe eating tiny trees when eating broccoli? Every day, Barracuda. Have I heard of not physics theory? No, sorry, not familiar with that. Cool. All right. So I think I didn't miss any questions. If you have any last-minute Q&A questions to ask before I say goodbye to you until next year or until the next, what was it, eclipse, I guess? Actually, there might be an announcement before the end of the year. We'll definitely do a stream if there's a big announcement from any astronomical facilities or science foundations. But any last questions? Because I'm probably going to be leaving in about 5 minutes. I need to go to bed. It's 2 a.m., 1:57. Yeah, cool. The best question, award for the best question goes to Mr. Barracuda for asking me if I can eat, if I dream of eating broccoli as a giraffe. And someone is asking me if I know how I say it. Do you know you say aliens in a funny way? No, I don't. You say aliens in a funny way. I say it the right way. That's how you say it. Aliens. Aliens. It's aliens. Say it with me. Aliens. Someone is asking me why am I so good at this? At what? I'm not good at this. I'm not good at streaming. I barely record well. I've been doing this since 2016 part-time. Then I started doing it full-time in 2020, so like 5 years full-time, and I'm still struggling. It's so difficult. You don't know how difficult it is. Do not ever become a YouTuber or any content creator. It's just so challenging. Okay. I'm reading some of the last comments, and someone is asking me about merch. You want to know about merch? Would you like to buy merch? Well, actually, yeah, I wanted to create a design with that asteroid, Anton Petrov asteroid, but it's still being worked on. I want it to be super funny, and it's mostly for me. It's not even for you to buy, but if you want to buy it, it's cool. It's going to have like a funny face. Let me see if I can actually find the picture. There was a student somewhere in California, undergraduate student who did not share his or her name, but he goes by K. Lee. And he created this incredible infographics with all of the funny asteroid pictures. And one of them has my face on it. I want to see if I have it here. Do I have it here? Let me see. It's so funny. I could not stop laughing. So I want to have that as a merch. Oh, I don't have it here. Anyway, it was in that video where I talked about the asteroid Anton Petrov. So that's going to be the next merch. And that... you don't have to buy. You really don't have to, but it helps. I get like about $3 off every purchase, in case you wondered. So, yeah. And also a lot of, I kind of stopped mentioning this, but a lot of the stuff I do when it comes to like merch, or if I ever do sponsorships, by the way, most of this goes to charities because I make enough from YouTube as it is, and I don't. The charity I've been supporting there's a Korean orphanage. So okay, in case you were not here in 2022, our family had a small tragedy. Our super young son passed away when he was only 3 months old, and ever since then I basically kind of committed to supporting a few orphanages here and there. And so many of the things that I make as an extra income, including Patreon and donations and stuff like that. Pretty much most of this, not like all of this, but most of this, like I would say 95% of this, usually goes to one of those orphanages. Just something that my wife and I do to feel better. It's been tough. It's been tough 3 years for us, but we're trying our best. And then, as some of you probably know, that I have a lot of family in Eastern Europe, Ukraine, Belarus, and Russia. And even though I don't know them that well, we all got affected by the war. So it's been pretty crazy 3 years for me. So yeah, just trying to survive. But anyway, so here's your answer to that merch question. It's coming, but it's going to be the funny face with the asteroid on it. Anyway, thank you so much, KFD. I really appreciate it. Thank you for the donation and for the comment. Someone is saying I should collaborate with famous asteroid YouTubers to make a series of My Asteroid is Better. That's actually a good one. I would love to do that. One person that has an asteroid named after her that I would love to collaborate with, or at least meet with, is Dr. Becky. She's awesome, but she's in England. I'm here in Korea. We've briefly chatted through like comments. We don't know each other very well, and she's awesome though. Her videos are really great. If you're not subscribed to her channel, definitely subscribe. And she has a asteroid that's just a little bit bigger than mine by like 100 meters. So yeah, she's cool. And also she has a legit PhD in astrophysics, which I don't. Okay, so any last questions before I go? Oh yeah, Scott Manley. Scott Manley has a bigger asteroid, and he's also pretty cool. But Scott Manley, he only does YouTube as part-time hobby. Literally, he works for Apple. He works for Apple, so he has better priorities there. He makes way more from Apple than he does from YouTube. Okay, cool. So I'm looking at any last important questions or comments, and also possibly anything about. Does anyone wants to know anything about Vera Rubin, or you missed anything? Did we talk about? We talked about the galactic curves, gravitational lensing. Oh, they actually did they show this picture? I forgot if they showed this picture. This was one of the images they released for the press for the media. This is the famous Trifid Nebula, and if you look at the original image, it looks nothing like this. Let me show you the original. Look at this, incomparable. The original, the new image. The original, the new image. So much better. So that's going to be the quality of this new telescope. Okay. Oh, there's some more questions. I see my name. What is my science degree? My degree was in microbiology and psychology, of all things. And then I did a degree in Masters of Science Education, which is why I started teaching science and math. And after this, I just realized academia was not for me. You need to be really good at academic politics to be good at academia. I was just not cut out for it. Do I know David Kipler from Cool Words? No, I've talked to him as well. He lives in the U.S. and he is at Columbia University. He actually did invite me to do a stream with him, but it is just super difficult because of the time zone differences. When he was available, it was 2 a.m. for me, 2 a.m. in the morning. When I was available, it was basically nighttime for him. Okay. What exists between the Higgs mass and the Planck mass? I cannot answer that. I'm sorry. I don't think there's anything there. That's not a question I can answer. If I discovered aliens, would I tell anyone? No. If I discovered aliens, if I actually discovered evidence of alien life on another planet, you would probably be hearing a lot about it already. Because I would be saying how wrong I was this whole time. All right, so I'm gonna close these pictures one by one before I log off. Let's see if I missed anything. Oh, here, did I talk about this? This was the pictures from this was a picture when the facility was being built, I think about 10 years ago. And we have this beautiful image of the, beautiful time lapse actually, of the Vera Rubin Observatory with the night sky above it. Then there's the website, which I will post later. And we have the observatory on top of the mountain. It's approximately 2,800 meters above the surface. Then we have Vera Rubin herself. That's the sensor, picture of the sensor. It's this is like roughly around, what was it, like 1 meter or something? 3 feet. Vera Rubin, when she was super young, this is around the same time when she discovered the rotation curves were slightly different from what was expected. Basically when she discovered dark matter. That's the mirror of the Vera Rubin telescope, the size of the mirror. Picture of the observatory during nighttime. And I think that, that's the first picture they released, and that's the nebula they released as well. Cool. So I think I pretty much covered most of the things I wanted to cover. And answered a lot of questions. Most of the questions, I think. Not all questions. Was there anything else I wanted to say before I go? I'm reading super quickly. Oh, fun fact. This made me laugh. So originally this observatory did not receive a lot of funding. It was actually funded by private funders. And one of them was Bill Gates. Yay. I'm sure people will love to hear that. I don't really care about Bill Gates, but I'm sure some people really don't like him. I don't know why. My chip is working fine. And one of them was a billionaire family by the family name Simoni. That's why this telescope sometimes is referred to as Simoni. Simoni Survey Telescope. They actually donated several $1 million. Okay, cool. I think I got everything covered. So I'm going to slowly walk away from this stream. Someone is asking me a last question about alien life. Which celestial body will most likely be the first to be discovered with non-Earth life? If we find something, anything ever, it's either going to be Mars or one of the icy moons of Jupiter or Saturn. I don't think we're going to find anything else anywhere else. So we're talking about Ganymede, Europa, probably Titan, but I don't think we'll find anything. But we'll see. Okay. I think I just saw the last question here. Where is it? Go to sleep. People are telling me, okay, I'm going to bed in 5 seconds. 3, 2, 1. All right. So I think I've covered everything. So thank you so much for coming and for staying with me for the last, 3 hours, I think. We're definitely, okay, I'm trying to promise another stream, but I can't because last time I promised this, it never happened. If there's an important announcement from NASA, from ESA, from Science Foundation, from really anyone, I'll definitely do a stream about it. However, because it's difficult to find topics on an actual stream as this one, I don't know if I'll be able to do it in the next few months, but I'll try. If there's time, I'll definitely do it. Anyway, thank you so much for coming. Thank you for all of the support and for great comments and for being wonderful. And honestly, just, stay wonderful and be nice because we do live through some difficult times. And keep smiling. There's a lot of stuff to look up to. So tomorrow there will probably not be no video, but I'll come back with a regular schedule on Tuesday, or I guess Monday maybe. And we'll discuss we'll be discussing new discoveries about the largest comet ever found. It's actually a pretty exciting study. And that comet will hopefully be imaged by this telescope very soon because it is one of the coolest objects discovered in the last few years. It was discovered in 2021. Stay wonderful. I'll see you tomorrow.